All right, let's get started. Welcome everyone to another webinar. Post Glover, neutral grounding resistors, tricks and treats. Hopefully you can recognize the theme. It's getting close. This is my daughter's favorite holiday, so I'm pretty excited for her at least. Anyway, so let's get started. My name is Chris Small. I am the Post Glover application, I should say a Post Glover application engineer, and also regional sales manager. I did graduate with an electrical engineering degree from Ohio State. Hopefully, if there's Michigan fans out there, you can forgive me. I've been at Post Glover for 12 years. Is that right? That sounds about right. This is actually an outdated picture. Oh, there it is. There's a little bit of resemblance, unfortunately, but it is what it is, right? All right. So, topics for review. Let's talk about what we're getting into today. Resistance grounding with parallel sources. Now, keep in mind, this is not an exhaustive list. This is only a 1-hour webinar. We'll probably go 45 minutes. But so here's some topics. If you guys have questions at the end, if I think on the send out we asked you guys a good question. So if you guys have any, great. We'll go through them. Hopefully, assuming we can answer them. If not, we will email you the answer. So, but parallel sources, automatic transfer switch, resistance grounding. We get a lot of questions about that. Also on the main time main, how does that work? What does it look like to do that as well? We're going to talk about sizing LRGs and HRGs, and then kind of go through those questions. So let's get started. Paralleled NGRs, separate grounding. So there's different ways to configure. This is with generators. It could be with transformers. I would say the only difference, honestly, there's going to be some harmonic issues potentially with generators that you wouldn't have from transformers, but otherwise they're going to act very similarly. So obviously I have generators pictured here. You could, for most intents purposes, you could switch those out with transformers. So you have a resistor at each and every source paralleled. That is one option. It's called separate grounding. We like this method. There's a lot of benefits to it. It depends. If there's a lot of generators, it may not be practical, because one of the issues with this method is that your ground fault current is additive. Okay, so let's say you had 200 amps for each generator. In this picture right here, you'd have a total of 600 amps of ground fault current. That in itself probably wouldn't be an issue, but let's say you had 10 of these things. You may need to go for a different, either much lower current or a different methodology here. So the good news is you have, no matter what you do, if you have one generator, two generators online, or all three, you're gonna have some form of ground fault protection, right? So you don't have to worry about what kind of configuration you're using in terms of how many generators. Maintenance is also achieved, because if you took one generator out with that corresponding resistor, the other two or whatever else, as each source has its own protection, you're good to go. So it doesn't really matter if you have one offline. You're gonna be off. It's not tied together, so you're gonna be able to safely maintenance that as well. Okay, so I think we covered that well enough. Let's talk about the next option. This is, to be honest, this is less common. The reason is because I would say there's more negatives. So the good news about this, so this, just to describe it here, as you can probably see, we have 3 generators. We have a shared XO with one resistor. And so, obviously cost is a benefit for this one. You have 1 versus 3 resistors, right? But you do have some issues with generators specifically. You have parallel gens, you have third harmonic contributions per gen. You're going to be dealing with third harmonics for this configuration for sure. So you have to worry about harmonics in this situation. The good news is, once again, you have one resistor. Let's say it's 400 amps. It's 400 amps no matter what you do, right? So it's a very consistent fault level. But not only the harmonics an issue, because everything's tied together. If, let's say you take out that leftmost generator, since the neutrals are tied together, if there's no fault condition, you're good to go. But if you get a fault condition, you're going to have some issues if you're trying to maintenance that generator. So you're in a situation where the maintenance guys may think that the generator is offline, but not really, because you get that fault and you're still live. So really the only option in this scenario is to maintenance it while you're completely offline. Let's go on to the next. So a different way to do this for a derived neutral. So what we're doing here, just to describe it, we have the same three generators. We have a this scenario, it's some kind of a neutral deriving transformer. That's what this box is right here, a neutral deriving transformer. And then because you're on a three wire bus typically, and then you have the resistor hanging off that. So the good news is you don't have a direct connection to the generator to neutral, so you don't have the harmonic issues you'd otherwise have. Also, because they're independent of each other, and the ground source, you don't have any maintenance issues. Just like the first one, you're going to be offline and good to go. But as you can probably tell, since this box here is the only ground fault path, when you're winding up and you're not quite dialed in yet on the generator, you're gonna be ungrounded, right? So that's the big negative for this one. This one is fairly common, but once again, the big negative is that wind up ungrounded. Some people can't tolerate that. So that's another option for paralleled NGRs with the derived neutral. And then we have a kind of the catch-all of scenarios. You have the hybrid system. Now we've gone through this. I actually had a webinar on this by itself, I believe. So we won't go into super detail on this one. Actually, that reminds me. If you guys, we've done, I think up to date, we've done like 14 or 15 webinars since COVID hit. We're all available on YouTube. So if there's a webinar you want to go to, just as a reminder, you can go back. So if you want to know more about hybrid, I'll briefly touch on it here. But if you want 45 minutes worth of it, go back to that one. So you have HRG per generator, okay, with typically 5 to 10 amps, 5 or 10 amps really, depending on how you want to size it. And honestly, for this scenario, the only thing you really need to worry about is the generator, because the HRG is per generator, and theoretically you would be disconnecting with the HRG. Really, the only thing you need to worry about is sizing. Because usually, when you have HRG, high resistance ground systems, you're worried about capacitive charging currents. In this scenario, you really only have to worry about that of the generator, which is not very much at all. So it's not really an issue typically, but just a common size would be 5 or 10 amps regardless. But anyway, so you have HRG per generator. You still have the derived neutral off of the bus, and then therefore you have an LRG here. Well, so this does a lot of different things. Okay, so first you have, just like the first one, you have, no matter what happens, you have some kind of ground protection. You don't ever have an unground system or anything like that. That's one thing. Another thing is this could potentially protect against stator faults in your generator. What I go into in my other webinar, essentially in a nutshell, is if you have differential relaying across that generator and you figure out that there is a fault within the generator itself, you can open that breaker, the generator breaker, and wind down with just, let's say, 5 amps of ground fault, which is going to be protecting, saving your generator from extra damage, which could happen easily with either. Obviously, solid ground would be horrible, but low resistance ground would probably, based on different papers, would also cause additional damage. So, if you just want to have, if you just want to have all the maintenance taken care of, and you want to have all the no matter what you do with your configuration, you always have ground fault. That's one reason to use the hybrid, but also it's for that generator protection as well. Because you're having for this example, 4 different resistors, a lot of times this is going to be at 15 kV. So there's going to be extra cost here. So that's the negative here. You're going to be you're going to be 2 to 3 times more than just your typical LRG, and then maybe twice as much as like if you did one per generator. Let's move on to automatic transfer switches. I get the question all the time. This literally happens probably once a month. Okay, so I have an engineer, and the engineer's like, well, look, the client really wants me to use one resistor, and I have this ATS, and I'm trying to figure out what configuration can I use one resistor. And the first thing I say is, well, are you sure you want to do that? I'm not saying you can't do it, and we're going to go into that in a second, but what we would recommend, and the most common way to do it, is you have a separately derived system. So NEC talks about, this is a clip from NEC. You have the NEC talks about you have separately derived and non-separately derived systems. All right, so you have so all it means is separately derived. Obviously, it's kind of how it sounds. You have 2 different systems, one on the utility service, one with your backup or emergency generator, and you're switching between the 2, and they're completely separate. You switch to neutral, you switch to 3 phases. You obviously need a 4-pole transfer switch for that. So there's 2 separate systems. That means 2 separate grounding systems. We recommend it this way because it's just the most flexible. It's the least amount of problems, but it does come with the problem that if you want resistance grounding for both sides, you're going to have to get 2 resistors because they're separate, right? Once again, just to go through these, maintenance is the same idea, right? You have one per side, one side's complete off at a certain point, so you can easily maintenance it. It is straightforward. It's 2 separate systems. But you know, if the client's really worried, or you're really worried about, you know, what typically would be, you know, $4,000 to $8,000 depending on the voltage, then hey, you know, there's another way to do it. Let's talk about it. Non-separately derived systems. NEC talks about how basically it's the exact same system. You have 2 separate sides, but instead of switching this 4th pole, you are having a direct contact here. So you just have a 3-pole transfer switch. You're just transferring your 3 phases, and you go from there. So because you're sharing that neutral, just like we were sharing it with the parallel generators, right? We have issues with maintenance. Okay, we can't. You're going to have to turn off the whole system essentially to maintenance this unit. Also labeling. NEC has requirements for this type of scenario. That's got a section on non-separately derived systems. You're going to have a lot of labeling, warning signs. Look, you know, this is hooked up. I mean, which is obviously you need, right? Because you have a maintenance guy who has no idea. You turn off his generator, he's got no idea that this thing's live without all these warning labels. So that's why they're all required. There's a lot of them, but that's just something that you have to deal with it if you want to do it this way. And once again, potential confusion. Maybe not. Maybe if you have a good understanding and obviously all the warning labels, maybe it's going to be fine. But that's kind of the negative. So I didn't mention it, but you would want to put the resistor on the load side of the ATS in this situation. Okay. Well, that's all I can say about that one. Let's stop for a second and do a poll question. And no, it does not have anything to do with what candy that is your favorite. Although, let's see, I think these are M&Ms, and this is where I'm from right here. M&Ms, that's a good one. I like M&Ms. This was 2020, FYI. I don't know if they come out with 2021. Okay, thank you. The poll question is up. I will stop talking so you can concentrate on the poll question. This one was apparently a thinker. I had
All right, we're at 75% or 80% now of listeners have responded. 22% are most concerned with relay coordination, 28% with lowering the available ground fault current, 40% both, 6% are still figuring this one out.
God, that's probably the post lever guys there probably. All right, thank you, sir. All right, let's go through. Let's keep going then. All right, so ATS, main time main, they're similar. Main time main gives you a little more flexibility. So let's first just talk about what it is, just in case you don't know. Some of you probably know more than I do. But anyway, the point is that you have typically double-end switchgear here. You have a main source over here on your left-hand side. You have a main source B on your right-hand side, and you have a tie in the middle. So main, tie, main. That's why it's called that. So what does this do? It gives you flexibility. As you can see, there's loads on both sides. So ideally, what you're basically running is two different sources, two separate systems. But let's say main A over here goes down, and so what would happen is you would close this breaker here, and you could support these loads over here with this secondary source, or at least secondary for these loads. Okay, so that's basically the idea. It gives you flexibility. You could use multiple loads on one or both or the other source. So what's the difference between the open transition and closed transition? Essentially, once you have this issue, when you're trying to get back and up and running, say your main A is now ready to up and operate, you are going to, with an open transition, you're going to be temporarily closing this, opening this, temporarily, which means these loads are going to be briefly just not in service while this is coming back on. So it's an open transition, which means you're not sharing the system, but you're going to be a brief disconnection here. Closed transition is basically you're operating in parallel. So you have this up and running, and then you're just going to bring this main online, main A online. And so for a brief moment, you're going to be in parallel before you open this back up. So I mean, the only real reason I bring this up is because depending on if you have open or closed transition, it may impact the way what you want to expect from a resistor if there's a fault, et cetera. But in terms of resistors and how you want to configure those, there's flexibility. This is like, in my opinion, there's a lot of flexibility in main time main. The only way you can keep that flexibility is by having two resistors on each side, or one resistor per side. There we go. So yeah, so that being said, that's kind of the way to do it. Now, if you did, once again, if you did have a closed transition, you may, if for some reason you got an immediate fault or whatever, you may have alarms from both sides of this thing. Or if you chose to operate it for both sides, it's possible. But anyway, but yeah, that's the way you want to do it. There's no really issues with paralleling these, even temporarily. That's not going to be a problem. You just need to expect that. Okay, so let's go into sizing HRGs. Two components for specification. I get this question a lot. If you guys are advanced, I apologize. This is going to be something you already know. But I just want to go over this real quick, and we're going to go into LRGs as well. So really, you only need to know two things: voltage and capacitive charging current. I don't really care how big your generator is. If it's like, a 10 MVA generator, it doesn't really matter, except for the fact that for a 10 MVA system, you're probably gonna have a much larger system, more wire, more loads. So I do care about how much wire there is, how much motor load you have, because it does impact the capacitive charging current. But these are the things you want to worry about. Okay, so sizing HRGs, just using Ohm's law, V equals IR. If you're an electrical engineer, this is day one, right? Voltage equals current times resistance. So as for an example, the customer is asking if they can use an HRG designed for 480 at 600. This actually happens a few times a year. Purchaser makes a mistake. They probably put down 600 volts. And most of the time people just assume that means 480 volts. Sometimes that does not, and so you have a wrongly designed HRG. So what happens is you basically have a 55.4 ohm resistor for intended at 277. That would be, your 5 amps. At 600 volts, this is the line of neutral voltage here, and you're going to have 6.3 amps. So not only are you running a little warmer and a little hotter than usual, and I'm not going to, honestly, theoretically, you could do this. Like with our system, you could do it. You're going to run hotter than you're supposed to, but you could do this. But once again, you're not expecting it to be 6.3 amps. That's kind of it's going to throw off all your current. So it's pretty simple math. I just wanted to bring this to you. That look, voltage is important. Obviously, at larger voltages like medium voltage, you're going to have insulation issues, clearance issues. So it's very important for that, obviously, as well. Capacitive charging current. I don't remember. I don't think we've done an actual webinar on this entire topic. Well, we did a webinar that went a lot more into detail on this, but I'm going to kind of play the edges this time around. But essentially, capacitive charge current is in every system you can think of. It doesn't matter any type of electrical system. You're going to have capacitive charging current. And what that is essentially is leakage current that naturally exists because there's naturally existing capacitances. So if you look at the definition, you have two conductors with an insulator in between. That's kind of describes a capacitor. There's naturally occurring things like motor windings, parallel cables, all types of things in your system that have these naturally occurring capacitances. That capacitance carries a charge, it carries current. So you're going to be having that naturally leaking current. So in an ungrounded system, like I mentioned here, overvoltages are potential on intermittent ground faults. In fact, I truly talked about how you have to 8 times your rated voltage, okay? That is also a problem with high resistance ground systems, assuming that you don't size it correctly. So obviously design consideration would be you have to have the resistor current to be greater than the system charging current or the current associated with the system's capacitance. So it is what it is, right? So you don't really have to worry about at low resistance ground because the capacitive charging current is never going to be that low or never going to be that high, excuse me. But you have to worry about a high resistance ground. So what does that mean? At low voltage, charge current is typically low. In fact, traditionally speaking, we don't worry about capacitive charging current. Okay, a lot of times designs are made off. Look, you just need a 5 amp resistor. Just don't worry. There's no analysis that is done. It's just that is what it is. I will say, as time has progressed and systems are getting more complicated, there's been engineers and specifications, requirements, etc., that are more thinking about this at low voltage. For example, data centers, I would definitely recommend not just saying, oh, 5 amp resistor, that's it. That's not a good idea. You're gonna have UPSs that could potentially carry a large amount of capacitive charging current and other things that could happen as well. So just as a general rule of thumb, in my opinion, there's no real IEEE recommendation here, but I would recommend, look, don't worry about doing an analysis at low voltage, but have some flexibility. Either a tappable resistor or a higher rated resistor. I do know that, for example, I think the PIP spec changed some of their recommendations from 5 amps to 10 amps, just to give that flexibility. What we do is we have a tappable resistor, which is obviously choices of what your resistance is. We have 5 or 6 different choices. And with our unit, we also have a measuring feature where you actually can measure it upon startup. So that's just that was what I would consider flexibility. I would recommend, if you're specifying your system, I'm not selling you our unit, but I would say I am selling flexibility. I think it's a good idea. All right, so at medium voltage, it's a different story. And I think some of you probably have had experience with this. I would say you have to do a charge current, okay, analysis. The charge current is going to be much higher, larger conductors, etc. You should have calculations to be done. Now, what happens if you're in feed and you don't have the information. Well, I would say just kind of budget yourself accordingly to the point where you could have the option for later. But a lot of times I would say, you could, if you can feasibly estimate the amount of wire lengths and sizes, you could probably do it. Wire lengths are about, wire in general is about 80% typical of your typical capacitive charging current. So if you know what your wire is, you have a large understanding of what that may be. And then there's current. It's not really. It's more of a design thought than a specifier. But I thought I'd throw it in here. At low voltage, 10 amps or less is considered safe by IEEE. So you don't have to worry about low voltage typically. Higher levels are rarely needed. That this is true. Now, if you have, I've only seen a couple different places where the charge current is very high. And I think most of them, if not all of them, have data centers. So, if you're working on a data center, maybe you might need to deal with this. But otherwise, you're not gonna really have to worry about low voltage. Medium voltage, elevated charging current is much more likely. And then you also need to, at some point, you need to start thinking to yourself, well, look, at what point does my continuous current and that voltage, the amount of energy I have, give me a risk to my system, or if I can have potential arc flash. I mean, this might go more into the category of where is my medium voltage high resistance ground system safe. Just so you guys are aware, for those of you who don't even know that medium voltage high resistance ground is a thing, it's been used forever in terms of like generator protection, stuff like that, but it's getting much more common as a system protection with the continuous service that you need to worry about. So when's this going to have a risk to my system? I think there's not a whole lot of division when it comes to 5 kV or below. It's typically fairly safe. You do need to worry about how often you're going to, how much you're going to continue to operate, and what kind of cabling you need for that. I mean, that's another ball of wax. But the point is that you need to make sure that you're designed properly. But it can be done. But when you get up to the higher voltages is where there's some dispute on whether or not it's safe or not. But then those are the things you need to consider. I just wanted to bring it up. So thinking about continuous service, or even like partial continuous service, like for example, if you're tripping within an hour, what does that look like? What do I need to do? And will my equipment be safe? Those are things you need to worry about. Let's go to poll question number 2. This one, if I remember correctly, it shouldn't be as hard. Me and my colleague here, and I'm sitting next to, we have a debate on candy corn and how good it is. So this one's for him.
We've stalled out. About 70% of people have answered.
The 30% are rolling their eyes, but go ahead.
More than likely. Roughly speaking, 20% ghosts, 20% witches, 60% candy corn.
Damn it. Still, apparently you're right. Okay, that's fine. All right. Let's continue. So let's talk about sizing LRGs. This is where there's more questions usually from all over the place. We get these daily, right? How do you size your LRG? When we talk about sizing, we're typically talking about like the amount of ground fault current we're looking to size it for. There are some references that I have found that talk about sizing resistance grounding. In my opinion, they're not really good for sizing resistance grounding because they're really talking about reactance. I think a lot of times we want to put these in the same category, which is really true. When he talks about protecting generators, you could use both, but if you're looking at exceeding 2,000 amps on a NGR, which is what 60% or 100% of your three-phase voltage fault, which is what these calculations are referring to, you're going to be above that usually. And that means really there's no question. Like if you just are looking to get the bare minimum of protection, you're probably going to not want a neutral grounding resistor, because that's when you're above 2,000 amps is when those things get really expensive. They get big. Essentially, what you're doing is you're transferring transferring electrical energy into heat, but you're suppressing it, right? So if I have a 5 amp resistor, I'm only getting 5 amps, but you are turning that energy into heat, right? So the point is that 2,000 amps and above, we're looking at big old NGRs, and then that's really where a reactor is more sufficient. But the point, that's really losing the point of what a neutral grounding resistor or low resistance ground is all about, right? You really want to limit the ground fault current. You want to assist with your relay coordination, and you may want to ride through some transient faults. Those are the things that I think of when I think of low resistance ground. So, I would just say, don't look at these papers when we're talking about sizing a low resistance ground. If you're looking to accomplish these goals that are down here, then you probably don't want to look at these papers. Now, if there's a paper out there, I'll be honest, if you guys found a paper out there that has a specific direction, I don't think it exists because it's hard to do. But if there is, I would love to see it. But best practices. So the goal is the lowest ground fault current level possible, right? I mean, you're trying to accomplish those goals. Relay coordination. The lower the current, the more easily those things are accomplished. Okay. With one caveat, let me back up. So there's two things that would benefit from. You do need to make sure that you have relay visibility throughout your system, right? So so for that purpose, the higher the current, the more easy you're going to see, right? So if I have a higher current, if I have a 4 amp ground fault current, it's going to be easier to see anywhere in my system a ground fault versus, let's say, a 100 amp system. But the point is, you kind of want to play the middle between these two. So one of the questions I have is, how much effort do you want to invest? And really, all I need to ask you is, is this your system or not? Essentially, system engineers, design engineers for the system, these are in my opinion, these are the people that should be answering this question in terms of sizing. And it's based on, once again, your ability to see a fault throughout your system, regardless of where it is, easily, and then also keeping that current low enough so you can get below damage curves, or you can limit yourself and more easily coordinate your relays. But one of the things I get all the time is, from a gen dealer, and no offense to gen dealer, but they're not the system engineer, they're not the design engineer, and they need to specify this current. Well, you should just throw all that stuff out the window, in my opinion, and say, look, I don't have intimate knowledge of a relay system and what its capabilities are and how far the faults are going to be, where all my motors are going to be, et cetera, et cetera. So I would just use common practice, which is, typically for 5 kV, we're talking about 100 to 400 amp resistors. When I say 100 to 400 amp, I just mean let through current, right? Ground fault current. 15 kV, 200 to 400 amps, those are most common for most applications. Now, this is not taking into consideration neutral current or continuous neutral current. We'll talk about that in a minute. But the point is that if you're not the system design, if you're not the design engineer, you may just want to look for common usage of what you typically use of that system. But we can help with that. We could definitely help with that. What about continuous current, like I just said? Well, so I've read a few papers, and maybe some of you have read as well, that a resistor can handle 10% of the rated 10-second current. So if you didn't know, the most common rating for neutral low resistance ground systems is 10 seconds, which comes with the IEEE requirement of a 760 C rise or less. And you can kind of see that if you have good enough eyes. I know it's kind of probably small on your screen. I have a big old screen, so I can see it pretty easily. 760 C here. So the point is that I'm not going to dispute that. I think it might be true generally speaking. But I also think it's kind of misleading, because you really don't, the goal is not really to operate 10% of the current continuously. The goal should be to operate 10% continuously and then also be able to handle a fault on top of that, because you're gonna, if you have a continuous current flowing, you obviously have a continuous temperature rating that's higher than ambient. And then so that you're gonna be adding to that when you have a fault. So that can be an issue, and you need to take that into consideration. I don't think a lot, well, I shouldn't say that. I think there's sometimes when that doesn't happen. That's a worry to me. I would say that the nameplate is key, only because if you were looking for a specific amount of continuous current and you just assume, or you ask the manufacturer, oh, can this handle this amount of current? First of all, you may not be taking into consideration the series of events I just laid out for you, but also, you know, I don't think you're going to be, I don't think you may not get what you want. Like, I wouldn't necessarily trust manufacturer for the information. That's not, I shouldn't say, that's not a good thing to say, but if it's not on the nameplate, why is it on the nameplate? It's like, if this can handle 100 amps continuous current, then why wouldn't you put it on the nameplate? So if you truly need that much, or I would say probably any more than 10 amps of current, I would maybe try to get it on the nameplate. Now, you may say, well, look, I'm just going to be using this for 2 seconds or less, and so I'm pretty sure this is going to be fine. I have 30 amps of continuous current. It's going to have a certain amount of degrees C rise, and I'm only going to be using this thing for 2 seconds. It's rated for 10 seconds, so I should be good. Okay, I'm not going to say criticize that level of engineering, except for the fact that just make sure that you don't think you know what those values are. What does your temperature curve look like for the NGR, and what does that continuous temperature look like for the NGR? And so if you know those things, then you can make that decision, no problem, right? Okay, so sizing, okay, best practices. Something that people don't necessarily worry about enough, in my opinion, is, does a resistor maintain its own value as it heats up? And the short answer is no, okay? The long answer is, for at least for materials that are used for resistors, the resistance will always go up as temperature rises. So, the more your resistor heats up, the more your resistance is going to be, which means the lower your current's going to be. Well, that can impact your relay settings, and it could potentially be an issue. So I would posit that if you want to have a tighter requirement, let's say, look, you are the system design engineer, I want these to be 100 amp resistors. I can worry about relay coordination. I can figure all this out. Well, the tighter you put that, essentially, I think the more you might need to worry about this, because you're gonna have to have this as a consideration. Now, so you have the temperature coefficient of resistivity, which is this, which actually is this specifically this, and so essentially you can figure this out. You're gonna get it from, it's based on material, right? So you're gonna get it from your manufacturer. Do you need to get it? No, not necessarily, but I would say this: the overall general IEEE guidelines for this are pretty loose. You could have a pretty large fluctuation. If I was designing a system, I would want to know what that is, or I would specify what, I would figure out what I want, or what common materials typically have that are materials that I want to use, and I would specify it, or I would just ask and make sure that they're high, they're low enough so that it's not just crazy insane swings, because once again, the IEEE guidelines are pretty loose. Okay, so other tips and tricks, and this is not an exhaustive list. This is stuff I could try to fit in 45 minutes. And once again, if you have questions about other types of stuff, we can talk about that. But you remove overvoltage protection from drives when using a resistance ground system. We've had enough drives go up in smoke to know that this is definitely something you want to think about. So you have an MOV protection. We're talking about a ground path on your system. Okay, it's going to be grounded. You're going to have a parallel path. It's going to be solidly grounded. You're going to get more current through that than you are through your resistor. Your drive is going to smoke. This is just not to get you panicked. Most of your drives have jumpers on them that can remove this feature, and so you can jumper that to the point where you're not using it. I haven't seen that many. I would say less than that I'm aware of. I would say probably less than 10, maybe less than 20. So throughout, that's over 10 years. So that's not a ton, but still it's enough to say, well, you should think about that. All resistance grounding requirements from the NEC are referenced in section 250. So some of you who know the NEC are like, duh, section 250 is like most of the grounding. But a lot of people ask me like, well, where can you reference resistance grounding? And I can point them to like 3 or 4 different sections, and most of them are in 250, 311. There's a 367. It doesn't matter. The point is, my point is here is that look, all the information you're going to need to know is in 250. It's either going to be referenced or it's going to be in 250. If you want to know one thing and want to know about resistance grounding, for those who care, that's the number you think about. If you want to think about one number, that's the one you think. Or you can just ask me. I'll send you photocopies of it. Don't worry. So when we're talking about doing medium voltage applications, this is the kind of thing I mentioned before. I get a lot of times I get medium voltage applications where they want to use high resistance ground, and they're like, okay, well, this is what I want to do. I'm like, okay, well, you want to do like a charge current analysis to make sure you can? And they're like, well, we don't have enough information at this point. So at that point, you either need to, if you have the ability to conservatively estimate those values, then go for it. If you don't, then I would just budget for the more expensive application, which would be the HRG, and then you can do either one after you get your calculation done. A lot of times when these are in feed, you're not going to have all the information you need. Another question I get all the time, or really it's a request. I get requests all the time for for a Delta HRG system or Delta LRG system, either one. And it's for a 3-phase 3-wire system. So the one line says 3-phase 3-wire. Everywhere is 3-phase 3-wire. But turns out that the generator is actually 3-phase 4-wire. Now you may not just know that from one line, but the point is that check to make sure. You don't want to buy a Delta NGR, especially if it's a high voltage, for an extra, you're probably spending an extra $10,000 to $20,000, then find out, oh, whoops, we didn't need it. So that's what comes up all the time. So that is it. To conclusion, obviously these are kind of certain situational things, but generally speaking, I just want some closing notes. Resistance grounding is a simple concept, but as you can see here, there are some nuances. There's more nuance than even we just discussed today. So just keep that in mind. It is grounding, so you really want to prioritize it, just because grounding is one of the most important things for an electrical application in terms of safety. But in practice, I'm not pointing fingers at all, I promise, but it seems to be deprioritized. I'm not, and it is what it is. I just want to bring it out. I'm obviously biased in my love for grounding / resistance grounding, but it's one of the things you want to make sure you got right, because it is important for safety. Okay, so let's see if we have any questions. And if hopefully we have at least a few. We'll see. What we got, Stu?
First of all, I want to give you kudos for sticking to your 45-minute presentation time limit. Well done, 44 minutes. I've got about 4 questions here that I've kind of culled from the herd to bring up. First one, in a 4.16 kV system, is there a rule of thumb, amps per kVA, to guesstimate the charging current for distribution transformers?
No. Not to my knowledge, I should say. So there is one at low voltage. I'm sure based on that question, you probably know that existence because you're referring to it that specifically. But there is one at low voltage. I know in IEEE. I'm not aware of one at medium voltage. I would say, just from personal experience, it's probably not a good idea to have a rule of thumb. There are a lot of variances, and the values are high enough that an extra, 500 feet of cable here, or an extra, it's just not, the contributions are much higher. And so your variances are going to be, you can't average it out. You really got to do case by case, and that's why you have to do the analysis.
This one I think is very relevant to, probably more to LRGs, but also HRGs. How much percentage-wise can the resistance vary as the materials heat up?
You probably better want to answer. I know it's greatly, it can be a lot, but I think you're the best person to answer this one.
I think if you're staying with what we call resistor grade alloys of stainless steel, you could be looking at a swing of around 30%. I know there's measures in place now to change the IEEE standards to limit that to around 30%, between 30 and 50%. If you were to go with something as simple as a 304 grade stainless steel, which if your spec simply calls out elements need to be made of stainless steel, you could have a swing as high as 80%. Of course, the problem with that being that, if you've got a 10 amp resistor, you set your relays for 5 seconds, you're expecting to see 400 amps. You may only have 150 amps going through the resistor by the time your time delay expires. The relay therefore won't see enough current to trip something offline, and you'll end up just burning the resistor up. This one I've never seen before, so I thought I'd bring it up. Does inductive reactance impact the overall system capacitance? Does it lower the system capacitance?
Well, based on the idea that, capacitance and they're basically opposites, and the fact that you can have grounding systems that can try to cancel out capacitance with inductance, I think theoretically you could say yes. Have I ever tried to calculate that on a system that doesn't have literal inductors? Yeah, no, I've never considered that in terms of capacitive charging current, no. But theoretically, if you wanted to try to, number one, just so you know, there are systems that exist that try to do exactly that. They try to balance, they basically try to make the overall system's capacitance zero by doing inverse inductance, or I should say inverse, but basically the opposite, which would be inductance. And so to cancel the capacitance out. So because that exists, if that's what you're going for, yes, you can do something like that. But no, I don't do anything with inductance in terms of capacitive charging current analysis.
And the last question that I wanted to bring out was for paralleled NGRs using a hybrid scheme. If there were a stator ground fault, so you've got a fault in your generator, would the generator breaker still need to be opened if you had low resistance grounding on the system?
So yes, I mean, I would say, so that's one of the reasons why, so one of the reasons why hybrid grounding exists is because, it's been 20 years, let's say it's been 20 years. 20 years ago, we had, pulp and paper industry had a lot of, they were very high on resistance grounding, low resistance grounding. They would use low resistance grounding, and so they had a situation, and there might be multiple examples, but this is one that was in IEEE paper, so I'm familiar with this one. So basically, they had low resistance ground, they got a fault, it happened to be a stator fault, and they got a lot more damage than they were expecting, okay? So what happens is, even if you have 400 amps flowing on your resistor, you still have to tolerate that through the wind down of the generator, because the generator is continuing to provide energy and also fault current throughout the wind down duration. So the answer is, do you have to have it? No, so a stator fault by definition is damage, right? If you have a low resistance ground system, you're going to get additional damage, okay? Just because of it just obviously depends on the amount of ground fault current. If you have a solid ground system, I'm guessing you would be sweeping up the remains of the generator. the point is that the only way that you can truly minimize the damage to the least possible amount, which would be defined as just the fault itself, would be to do the hybrid grounding system, because 400 amps for whatever the wind down is going to be detrimental. There's a paper on it. I can refer to that as well. But basically, it's you get that decay current going through the system. You're going to create additional damage. The question becomes, how big are my generators? I have additional costs for the hybrid grounding system. Let's just say twice as much, because on average that's probably about right. Is that worth it? Is that doubling of cost, let's say it goes from 20 grand to 40 grand, depending on how many generators you have in parallel. Is that cost worth the extra protection? How likely is it for me to get a state of fault? How new are my generators, et cetera, et cetera? The more expensive your generators are, the older your generators are, the more likely that answer is yes. It's just a cost benefit analysis.
And that's our round of questions.
All right. If we missed any, or if there's some specific that that come late or whatever, we'll make sure to go ahead and email you the answer. I really appreciate your time. Next month we're going to be talking about we're talking about the highs and lows of fan cool DB. So get it, highs and lows. That's my bad humor. But Stu will be doing that presentation, and hopefully you guys are looking to come to that one as well. That will be next month. I appreciate you guys' time. Thank you very much, and we'll see you soon.